Welcome to the Michelson-Morley experiment. In 1678, Huygens published his treatise on light, and in it he mentioned the luminiferous ether. Sometimes just referred to as the ether. And this is the matter that light is supposed to be travelling through. At the time, it was known that waves require a material to travel through, and this was the name given to the material that it was assumed light was travelling through. Because it had not yet been detected, it was thought that this luminiferous ether might have some very unusual properties. In 1849, Fizeau did his experiment measuring the speed of light in air. And in 1851, he did a similar experiment measuring the speed of light through moving water. This is the equipment that he used. This equipment consists of a light source, a beam splitter, which is a half-silvered mirror, two lenses, and a mirror. There was also a tube of running water. With the water running in and out. The direction of the water was important because Fizeau wanted to compare the light that was moving against and with the flow of water. One of the light rays will have shone from the light source, have been reflected by the beam splitter towards the lens, and then redirected through the water, moving against the flow of water. When it arrives at the second lens, it is directed towards the mirror. It is reflected off the mirror and into the lens, where it is directed against the flow of water. It returns to the first lens and is shone through the beam splitter to the observer. The other light ray would shine from the light source and hit the beam splitter and be reflected into the lens. It would then travel with the flow of water, come into contact with the second lens, reflect off the mirror, through the lens, return with the flow of water through the first lens and out through the beam splitter to the observer. The two light rays come from the same light source, so are coherent. When they arrive at the observer, they should interfere, and the interference pattern told Fizeau whether light travelled faster, flowing with the flow of water, and slower, flowing against. This was his prediction, and this is the result that he got. He observed that light moving with the flow of water travelled faster, and that light moving against the flow of water travelled slower, but not by as much as he had predicted. And unusually, the effect was greater for light moving against the flow of water. 30 years later, in 1881, Michelson tried to replicate these results. And he did so using a piece of equipment that he had designed called the Michelson interferometer. The interferometer consisted of a light source. It consisted of a beam splitter, which sent light to various mirrors and then back again, and into an eyepiece, where the interference pattern could be observed. Unfortunately, the uncertainties in his experiment were so large that they masked any result that he would have measured. So in 1885, he teamed up with Morley to conduct the famous Michelson-Morley experiment. Some of the improvements they made were setting up the equipment in a stone building in the basement. And this helped to eliminate any thermal and vibrational effects. They also set up the equipment on a sandstone block. Which was floating on a pool of mercury, further isolating it from vibrational effects. Even with all these precautions, they still had to sometimes pause the experiment because of vibrations coming from nearby thunderstorms and horse-drawn carriages in the street above. The aim of the experiment was to measure the relative velocity of luminiferous ether compared to the Earth, otherwise known as the ether wind. It was thought that as the Earth moves through space, it is pushing its way through a cloud of ether, and therefore there should be a current of ether across the surface of the Earth. The aim of their experiment was to measure the speed of light in 2 perpendicular directions, and then to rotate the equipment until a difference was noticed. The difference being caused by the direction of the ether wind. Here is one of the original diagrams from their paper. We have the light source here at A, a beam splitter here at location B, where some of the light will reflect in this direction, and the rest of the light will be transmitted through this direction. The silvered surface is on the back of this piece of glass, so the light hitting and reflecting is travelling through the glass twice, and the light that is being transmitted through is only travelling through that thickness once. So there is an additional piece of glass here to counteract that possible effect. The light that is reflected would travel this way and reach a mirror here at D and return along this path, reaching this mirror, reflecting back to this mirror, and it would keep going all the way to this mirror here at E, at which point it would retrace its path all the way back to the beam splitter. And on arriving at the beam splitter, some of the light would arrive at the microscope. Light that does not reflect at the beam splitter and carries on reflects at this mirror and this one, and it would continue reflecting until it gets to this mirror here at E, at which point it would reflect back all the way through those mirrors, arriving back at the beam splitter and reflecting into the microscope. The 2 beams are travelling the same path length, and they are from the same light source, so they are coherent. This means that there will be an interference pattern. If the speed of light in one direction is different from the speed of light in the other direction, then the fringes observed at the microscope will be offset. It was predicted that there would be an offset of 0.4 of a fringe width. So the equipment was designed with an experimental error of only 0.1 fringe widths. The result that was observed, which is a null result or a zero result. This is often referred to as the most famous failed experiment in history. Other scientists attempted these experiments using their own equipment and got similar results. For example, Troughton and Noble in 1903 and Rayleigh and Brace in 1902-4. The experiment has been repeated many times through history and is still repeated to this day. The result is always the same, that the speed of light in any direction, irrespective of the movement of the Earth, is the same. It is invariant. The speed of light is constant, no matter how you, the observer, or the source, is traveling. It was results like these that led Einstein to create his special theory of relativity. It's worth noting that Michelson's interferometer is still used today. The equipment has been modernized and is used in very important experiments. For example, at the LIGO, the Laser Interferometry Gravitational Wave Observatory. This piece of equipment was able to successfully detect the first ever gravitational wave